Okay, off we go. A last reminder, don't forget about the attendance quiz. Here's the code. Make sure to confirm you get the score, et cetera, et cetera. Okay, picking up where we left off, here's a formula that we wrote down previously. This is the general formula for a linear approximation. Notice this is sort of the fully general case where we have a multivariable function that is also vector valued, right? Okay, so a couple of quick, easy little observations. I mean, the value of f and the value of L agree at the point A, so I can make this little change right here, a little micro change. You can also take this L and subtract it over to the other side of the equation. I mean, no big deal there, right? Hardly anything has happened. And yet, notice we now have a different take on what the derivative matrix is. Right? The derivative matrix you see now, you can view as taking how much you're changing the input, right? And df multiplies by how much you're changing the input to result in a linear estimate of how much that changes the output. Right? So this df thing, whatever it is, it turns input changes into output changes. Right? That's our cornerstone point of view on what is a derivative. So very reasonably, I think, df, because it turns input changes into output changes, should be called the derivative. And in fact, that is pretty common terminology. I'm going to try to get this all in the same. Well, let's see. Maybe I can go full screen. Well, still going to have to. Okay, here we go. df is called very often the derivative. It's a little bit weird. It's a little bit sort of contrary to our experience. I mean, in single variable calculus, we get really accustomed to the idea of thinking of the derivative as being a scalar. We associate it to scalar concepts like speed and slope, right? So in the multivariable setting, you kind of have to let go of those points of view. I mean, again, partial derivatives, yes, and et cetera, et cetera. But fundamentally, what a derivative is in a multivariable vector-valued context is not a scalar. It turns input changes into output changes, and those are both vectors. So df is a matrix. So anyway, it's a new point of view. By the way, little terminology. Sometimes it's called the derivative matrix. Sometimes it's called the derivative transformation because, of course, it's a linear transformation. And side note, it is also sometimes called the Jacobian matrix for kind of historical reasons. And as such, it's sometimes written JF. That notation gets used in different ways in different circumstances. So anyway, there you go. I think this is a really important point of view on the derivative matrix. Previously, we had observed that, hey, check it out. It's playing kind of a role analogous to the role that the derivative played in single variable linear approximations. And that was somewhat compelling, arguably. I think this is more compelling. It's literally doing exactly what derivatives are supposed to do. Okay. All right, a little bit of more terminology. When you talk about a change in the input, that's very often called a differential. So we're going to write that as dr. Excuse me. And likewise, in the outputs, when you talk about, well, let's be careful with this. This is not telling you how much the function changes, but it's telling you how much the linear approximation changes. AKA, it's a linear estimate of how much the function in question changes. And as such, that's called a differential. The output differential, we'll write that as df. So arguably a more compact and arguably more natural take on how to think about this is this alternative notation right here. Okay. All right, so let's draw a picture of this just to make sure we see visually how we're supposed to be thinking about this. If you have a multivariable function, for example, if we have a point there, and we plug that into some function, and then we get its image there, and if I think of the function as taking an input point to an output point. Right now, y'all will recognize this is not a graph, it's not a level set, right? This is that literal picture of a function that I like, and that's very common in math, and that we're going to make a lot of use of. DF also kind of shows up on this picture in the sense that it doesn't take points to points, but it takes changes, input changes to output changes. And so it doesn't take the point to the point, but it takes this vector to that vector. I think it's a really natural way to think about the derivative matrix. So that's nice. Okay, here's another way you can think about it. Now, we have the formula here written down on the previous page. It's just a recopy. Nothing happened there. And I'm going to make the innocent observation that, hey, how about, here's a crazy idea. Why don't I just divide both sides by dt? And I'm sweeping formalities under the rug that we don't need to worry about. You divide both sides by dt, and now let's look instead at this equation. And, what sense would we make out of dr dt? That's the time derivative of position. Wouldn't you be naturally inclined to call that a velocity? All right, we're going to make more sense out of that in a few minutes. Half an hour or so. So dr dt, rate of change of position, is velocity. And then analogously, the rate of change of your output position, df dt, output velocity. Right, so alternative take on what the derivative matrix does is it's what turns not a input change to an output change, but what turns an input rate of change into an output rate of change. And these being instantaneous rates of change, instantaneous velocities, there's no asterisk on this point of view that, this is an approximation, and of course linear estimates are never perfect. No, this is exact. For a differentiable function, this is exact. So, in fact, even though it's arguably sort of the second take that I'm giving you on how to think about the derivative matrix, this is actually my favorite take, because no approximations required. This is how I tend to think of derivative matrices, as relationship between input velocity and output velocity. Okay. All right. Last observation I'm going to make, and this is just kind of more of the same. Again, hardly anything is going to happen here. If we had a real valued function, previously we were considering the general case, vector valued, multivariable and vector valued. If it were real valued, I would have this alternative. Instead of writing the derivative matrix, it'd be a matrix with a single row, and I can reinterpret that as a dot product with the gradient. This is our alternative take on the real valued case. And again, input changes and output changes, that's all kind of the same. Nothing really particularly different there. And so we get, again, this kind of new interpretation of the gradient, and to be specific, dot product with the gradient. That too is a relationship between input velocities and output velocities, or input changes and output changes. Take your pick. Right? So, whether this is an input change or an input velocity, your choice. Likewise, output change or output velocity, and I can't emphasize enough, this is real valued only. This only makes sense. You can only talk about dot products with the gradient in the real valued case. Dot product with the gradient behaves just like multiplying by the derivative matrix. And by the way, there's nothing spooky about this. If you just look at how you write these down, how would I write down a dot product with the gradient? Well, the gradient vector is going to have, let's say, 3 elements if there's 3 variables, right? And you're going to dot product with input change, which will have 3 elements, and dot product, you multiply and add. In this case, the derivative matrix, still the same 3 elements, just kind of written sideways, right? And whether you whether you matrix multiply or vector dot product, it's the same exact arithmetic, right? It's just sort of an alternative, how do you prefer to think about it? So again, just an option. You don't have to think of it this way, but sometimes it's convenient. Sometimes it's convenient not to think about this as a matrix, but instead to think about it as a vector. And we'll talk about some of those different scenarios as we move along. Okay. All right, so that finishes 2.3. Moving along to 2.4. 2.4 has kind of a lot of boring stuff in it. I think it's mostly pretty straight read. I'm going to hit the highlights as usual. And there is one part of it that's really actually quite challenging that we will talk about in great detail. This is one of the first parts that I feel like we need to talk about. I say D is linear, and it is very easy to misunderstand what we mean by this. If I say differentiation is linear, a lot of students would say, well, yeah, of course it is. It's a matrix. Look at this. DF being a matrix, of course it's linear. All matrices are linear. So whatever input changes to whatever output changes, multiplying by a matrix is always linear. Why are we restating that this is linear? Okay, that completely misses the point here. Of course DF is linear. Yes, DF is a matrix. Absolutely. That's not what I'm talking about. I'm not talking about DF. I'm talking about D. Right? So D is a function that takes as its input a differentiable multivariable vector valued function and gives as its output the m by n matrix that is the derivative matrix. So yeah, of course DF is linear. That's obvious. What's not obvious is that the act of differentiation, the act of you give me a function, I give you a derivative matrix, that is linear. And that's very much not the same statement. How are we doing? Is everybody with me on the distinction there? Okay. So when I say that D is linear, D acts on functions. So this is a statement about what happens when you put in a linear combination of functions. When you take a derivative of a linear combination of functions, the linearity of D is telling you that you get the same linear combination of the individual derivatives. Again, totally different statement. Okay, and then there's an example. If you want to see, exactly what, what does this feel like? What does it look like? An example. Here, I gave you a couple functions, and you can, on the one hand, take a linear combination of the functions. You can, on the other hand, take the same linear combination of their derivatives, and you're going to get the same thing either way. So make sure to read through these details. This is just an explicit fleshing out of exactly what this says right here. Alrighty. And then a quick reference. This is, boring but necessary. Again, this is the perfect candidate for y'all to read. Differentiation has kind of a product rule, kind of a quotient rule that apply in appropriate cases, and they're written down in the book. And the way you prove them is by just writing everything out in terms of coordinates. And it's just kind of boring tedium. But it is nice to know those rules, so make sure to check those rules out. Make sure you have them, in your toolbox for possible use. Okay. All right. Next thing. Higher order partials. Again, there's a lot of boring parts of this. So let me go quickly through, what do we mean by higher order partial? And good news, it's a very familiar idea. It's just like higher order derivatives in Calc 1. It's really no big deal. Think back to Calc 1. If you've got a function, you take a derivative of it, you get another function, which you can then take a derivative of again. That's all it is, right? So same deal. If you have a multivariable function and you take a partial derivative of it, notice that what you get is another multivariable function. And you could talk about taking partials of it. That's all it is. Now, there are questions as to what this looks like. There's some things to say about notation, but ultimately, as to what is a higher order partial, that's all it is, just like a higher order single variable derivative. So let's talk about the notation a little bit. This is a little bit awkward. It's a frustrating reality that is unavoidable given the notations we've selected. So here we go. If I have a function f, and if I do the x partial of that function, we write the x partial you'll notice on the left side of the function. That's just how we write it. And then if I take a y partial of that, and then of course that's on the left side because we're taking the y partial of what we've already taken the x partial. Okay, so as a result, the partial y is on the left and the partial x is on the right. And here's the confusing, frustrating alternative option, same function. Again, I'm going to first take the partial with respect to x. And then whatever I get, I'm going to second take the partial with respect to y. Notice now that the x is on the left and the y is on the right. And if you look at this versus that, it's seemingly backwards. You see what I mean? Look, you kind of have to, right? this is, what am I going to do, right? This is fyx. It wouldn't seem to be right. And then likewise up here. So ultimately, who's to blame for this outrage? Our pre-existing notations, the fact that the Leibniz notation is on the left, but the subscript sort of Newton-like notation is on the right. That's what's to blame, ultimately. So, this is what we must deal with. So, make sure to be aware, make sure to always think it through. You cannot have a single rule that says whichever one's on the left acts first. Nope. It's just not. And like vice versa the other way. Okay. All right. Is everybody doing all right? Okay. Here's a weird coincidence you may have noticed. If you switch the order of the derivatives, you get the same result. Weird. Now, if you were to write down the power rule and apply it, x partial, y partial, to, let's say, a monomial, it's really not hard to prove that this will always work for any monomial. It's also not hard to prove that it'll, of course, work for any polynomial. What's not immediately obvious is that this works for a much broader category of functions. Not just polynomial. It's not just a matter of, you see how the power rule works and this is always... No, it's for exponentials and logs and trig functions and all sorts of weird kinds of other functions. The same thing keeps working. Where those functions are defined, of course. In fact, we have a theorem that under certain conditions that I'll come back and talk about in a moment, if you just rearrange the order in which you take the various partials, and by the way, I know the notation here is a little bit annoying, a little bit opaque. Just take your time, think about what every individual thing means, and I think you can convince yourself. That's all this is saying. This is just a fancy way, formal way of writing down, reorder the order that you're doing the partials. And you get the same thing. So broad category of functions. Now, there is, again, a condition. There's a catch. It does not always work. There are counterexamples. Here's the condition. The function in question, if you're talking about kth order partials, the function has to be ck. Now, what we mean by ck, it's a reference to the fact that the function has to be continuous, and furthermore, all kth order partials also have to be continuous. Right, that's what CK means. It's just a definition. It's a very useful notation, by the way. There's lots of circumstances where you need to know that the function is C2 or C1 or something like that. Right? By the way, if you think about it, then C0 would just mean continuous. So it's a very common notation. You're going to see CK, particularly C1 and C2, quite a bit in this course and in other courses. So make sure to digest that idea. Anyway, that's the condition. That's what we need in order to be able to draw this conclusion about rearrangements. Okay. Now you might be thinking to yourself, well, then this is a useless theorem. How is it useful to me to know that the order doesn't matter if I have to take all of those partials explicitly anyway to confirm that they exist and are continuous? If I've already got them computed, then I can just eyeball observe that these are all the same. What do we gain by writing this as a theorem? Right? And the answer is you, in fact, do not have to actually compute all of those partials. You just need to observe that they exist and that they're continuous, and sometimes that's really, really obvious. So for example, if you have a product of exponentials and polynomials and sines and cosines, all of the partials of the partials, no matter how many partials you take, are always going to be combinations of exponentials, polynomials, and sines and cosines. And those, of course, all exist and they're all continuous. Right? So very often, checking that something is CK is kind of a freebie. And so then you get a powerful result without any significant effort. Does that make sense to everybody? How are we doing? Questions? Feel free. Okay. All right. Here's where things get a little weird. What do second partials look like? Now, I want to emphasize, we're going to, it depends on what kind of a picture you're looking at. We're going to consider graphs. So what we're looking at here in particular, this is a graph of a function of x and y, some function. I've deliberately made it look like a Pringle. And so what we're about to investigate here, what do second partials look like, right? Second partials are a matter of calculus. We're interested in what that looks like on graphs. So what we're about to do here is we're about to add to our understanding of the calculus of graphs. Reminder, that means 0 about level sets. It means 0 about parametrized curves. Right? This is just in the graph setting. Okay, and in that setting, all right, well, let's think it through. How would I compute, for example, fxx? Well, we have rules. The way we compute fxx, well, we take the first thing you're going to have to do is hold y constant. Right, let's draw a picture of that, holding y constant. Right, cross-section, a vertical cross-section parallel to the x-axis. So we're looking then at this curve, that is that cross-section of that Pringle. And fxx says, okay, this, what you might call partial function, right? The single variable function you get when x is the only variable that you're entertaining as a variable. You just take its derivative twice. And we already know what that looks like. We already know that when you take a derivative twice, concave down corresponds to that second derivative being negative. Is that cool? Everybody happy with that? All right, so likewise for FYY, and I'm going to let you all think through the picture. The punchline is going to be that we'll be looking at this curve. Make sure to think that through. Make sure you're comfortable with that. And notice this is not concave down, this is concave up. Concave up corresponds to that partial being positive. Right, so it's a little bit weird. I mean, we're accustomed to having a single notion of concavity. It's either concave up or concave down. What we see here is that when you have two variables, we've got already two separate notions of concavity, one in the x direction, one in the y direction. And the unmixed second partials, xx and yy second partials, speak to those concavities exactly like you would expect. Okay, is everybody all right with that? I'm going to call this good news. Right? If you were going to guess, without having done any analysis, if you were going to guess how to interpret those second partials, this might very well be your guess. So I like it when guesses turn out to be true. That's intuitively satisfying, I think. Here's the weird one. What if I have a mixed second partial? How do you interpret that? And can we make a reasonable guess without actually doing the analysis? Right? So what would be, thinking back to single variable calculus, what's the single variable analog of a mixed second partial? And there is none. Because in single variable calculus, there's only one input variable. There is nothing to mix it with. Right? So do not look to your single variable calculus experience for guidance on how you might guess what this is. There is no single variable analog. We're in uncharted territory, and we have to figure this out from first principles. So, all right. Now, here's an awkward reality. The picture on this is hard to draw, and I spent a lot of time trying and failing, and I eventually came to the conclusion it's better off just not even drawing the graph itself. But let me remind you, this function that we're looking at, let's see here, let me use purple, this function, of which we're going to do a second partial, what we're looking at here is the graph of that function. Right, so can't emphasize enough, this is the graph of f that we're looking at. Now I'm just not going to draw that corresponding surface. It'll just mess up the picture as it turns out. So you're going to have to kind of imagine there being a surface here, and then we're going to look at various tangent lines and stuff like that. Okay. All right, so let's try to make sense out of, let's see here. Apparently we're going to do the y partial of that function f. And this is something I can easily make an interpretation of. We already have the interpretation. If you're looking at a graph of f, the y partial just says, okay, vertical cross sections in the y direction, slope of the tangent line. That's it. So, for example, looking at, let's say a point like this, let's just say, we're going to look at moving in, wrong color, sorry. Moving in the y direction. And again, there's some graph up here that I'm not going to draw because it just makes it more confusing. But whatever that surface is, it's going to have a cross section in that direction, and I'm going to say, let's pretend that that's it. So, what is the y partial? This thing right here, that's the slope of that tangent line in the y direction. Okay. Here's where things get confusing. I now want to talk about what is the x partial of that y partial. You're going to feel a temptation to write this in terms of a slope or something. And you can't. This is where you have to be very, very careful not to conflate the calculus of graphs with the calculus of not a graph. Okay? This x partial, the thing I'm taking the x partial of, I'm not looking at a graph of it. I'm looking at a graph of f. I'm taking the x partial of the partial of f with respect to y. I'm simply not looking at a graph of the partial of f with respect to y. So I cannot apply the calculus of graphs to this x partial. Just can't do it. So that x partial we cannot think of as a slope. Is everybody comfortable with that? I mean, again, that's a landmine. That'll give you all sorts of garbage nonsense answers. Okay, well, how are we gonna, oh my gosh, how are we gonna think about this? We just have this other point of view on partials with respect to x. I can think of a partial as a rate of change as you move in that x direction. No graph required, right? So as I move in the x direction, as I do like this, as I come out of the screen, as it were, right? How do these slopes change? Always slopes in the y direction, but how do those y direction slopes change as I move in the x direction? And so let's think through that process, and I'm just going to draw some actual slopes. Back here, that y direction slope, I'm going to say, that slope is about -2-ish, ballpark, just eyeball glance, something like that, right? And then for this one, it's more like -1. And then for this next one, it's about -0.5. And then for this next one, it's about 0. And for this next one, it's about +0.5. Right? So now let's just put it all together. I'm interested in these y slopes. I'm interested in these numbers that we just talked through. How are they changing as I move in the x direction? And I propose, as I move in the x direction, these y direction slopes are increasing. Is that cool? Because they're negative back here, then they're less negative, and then they're positive. That's increasing. So altogether then, this x partial of the y partials, namely this mixed second partial, is positive. It's confusing, isn't it? It's very confusing. This is geometrically very challenging, right? So if this is not taking in your head, right, then remember you can come back and listen to this video again, later. Give yourself some time, talk to some people about it, draw some pictures, talk to people again, listen to the video again. Might make more sense, right? But it's a lot to digest. So let's draw our conclusion then. What I have here is a kind of a suggestion of a picture of what it looks like when this mixed second partial is positive. And how would I describe this picture? Well, I'm going to do a sort of a hand gesture here. It's like as I come out of the page, the slopes of these y direction tangent lines, these slopes are doing like this. And I would call that a twisting of the surface, right? It's like I'm grabbing onto four corners of a sheet of rubber and I'm putting literally a twist in that sheet of rubber. Is everybody happy with that? So that's pretty weird. There again is no Calc 1 version of it, but I think this is a pretty reasonable take. That mixed second partials indicate a twisting of the graph. Very geometrically challenging. Again, give yourself the time, digest as might be needed. Okay. All right, so that's section 2.4. Again, lots of other details. Make sure to read, et cetera, et cetera. I'm going to jump now up to section 3.1. This is because I need the conclusion that we're about to use. That we're about to sort of demonstrate here in 3.1. I need this for the way I like to treat section 2.5. So this is one of the little rearrangements that I do in the book. Let me remind you that on the class syllabus, on the class website, right? I have the content syllabus, and then what I call Bray reordering. Right, so the way I reorder the sections, and in the Bray reordering content syllabus, 2.4 is followed by 3.1, which is followed by 2.5, and that's exactly what we're doing here. Okay. Alrighty, so let's talk about parametric curves. for a second here. Y'all know what a parametric curve is, right? Position's a function of a parameter. Position in space is a function of a single parameter, usually thought of as time. And of course, this is how we write it sometimes. We just explicitly list the coordinate functions. Okay, so if I had a function like this, how would I write down the derivative matrix? And well, there's only one input variable. Input variables correspond to columns. If you only have one input variable, you're only going to have one column. So we have a weird shaped derivative matrix. It is a single column matrix. Now, I think it's kind of cool to observe that if I were to just kind of think from single variable calculus, and everybody remembers a formula like this for how to compute single variable derivatives, right? Well, for single variable functions, this actually works just fine. We don't need to get all fancy with definitions. It makes perfect sense. Because since there's only one input variable, there's only one coordinate, you might say, in the denominator that represents how much we're changing the input. And we're just dividing by a scalar. Right now, if this were a multivariable function, we'd have a vector in the denominator. That doesn't make any sense at all. You can't do this in a multivariable setting. But for a single variable function, it's fine. No problem. Turns out, these are the same, which is very satisfying. So how do we make sense out of this? I mean, geometrically, again, for a parametric curve. Now, again, let me remind you, I know I make a big deal about this a lot. You got to partition in your mind the calculus of graphs, not to be conflated with the calculus of level sets, not to be conflated with the calculus of parameterizations. We're about to learn something about the calculus of parameterizations. So, said differently, this is not the calculus of graphs. You can't apply this to graphs. So again, partitions in your mind, keep these ideas separate. So let's kind of look at what we have here. Let's see here. I've got some point on the curve at time t, and then h seconds later I've got some other point like that, and I can talk about subtracting them. The difference is going to be a vector like so. And then when you divide by h, you're going to get, well, let's say a slightly shorter vector, right? So you get vectors. These, let's do it like this. These expressions like this are vectors kind of like that. And y'all, I'm sure y'all recall in single variable calculus, when h approaches 0, you talk about the limit as h approaching 0 here. These lines that I'm sure you remember the term secant lines, as h gets smaller and smaller, these points get closer and closer. That line becomes more and more like a tangent line. And in the limit, let's see here, in the limit, we will actually have a vector in the direction of that tangent line. We'll have a vector that is pointing exactly the direction that the curve is going. Or you might say, keeping in mind a parametric curve kind of represents the motion of position, right? You might say that this represents the direction of motion of the parameterization. Is that cool? Okay. Not a slope, right? Some of this is kind of familiar, right? A lot of the ideas, secant lines, tangent lines, limit as h goes, a lot of that sounds like what we learned back in Calc 1. But this is not a slope because we're not looking at a graph. So again, be careful about that. Okay, so we have ourselves a vector pointing in the direction of motion, and I'm also going to point out, if you think about the magnitude of that is a distance. The magnitude of this represents an amount of time. This is distance per unit time. If you're talking about the magnitude, as far as magnitude is concerned, that's distance per unit time, and that is speed. So altogether then, what we have here is a vector this derivative thing is a vector that points in the direction of motion and whose magnitude is the speed, and that's the definition of velocity. So it works out really, really nicely that for a parametric curve or for a parameterization, the derivative is the velocity. Everybody buying it? It's not a slope, it's a velocity. It's not a scalar, it's a vector. Yeah? Feel free, again, if you have a question, feel free. Everybody's good? Okay. All right. So here's my recently acquired favorite next example. And by the way, this is part of what it's like to be a mathematician is you're constantly learning little things. And this is something that I could have learned, when I was taking multivariable calculus, but no one ever pointed it out. And this is very clever. And I don't know, I just never thought about it. And then somebody showed me this within the last few months. This is something that I just recently learned. So it's a beautiful observation. So y'all know the unit circle. Y'all know the unit circle is how you define trig. Right? The x-coordinate is cosine and the y-coordinate is sine. It's really the best way to think about the definitions of the trig functions. Specifically, where we understand t, well, let's do it like this. T, we understand to be the angle, but of course on a unit circle, an angle is a distance. So I claim that this parametric curve, the motion here of this point, aka that position vector, the motion of this point as parameterized there, I claim that it has unit speed. Because if we're talking about distance per unit time, okay, well, yeah, but if time is distance, then we're talking about distance per unit distance, and that's, of course, 1. Right, so this parametric curve right here is literally a unit speed parameterized curve. Okay, all right. All right, so let's see here. Next observation. I know that wherever I might happen to be on that curve, I know we've got this thing called the velocity vector. The velocity vector is points in the direction the curve is going, right? And the magnitude is the speed. Wait a minute, we just talked about this. The speed is 1. Oh, wait a second. We also have talked about how this is the unit circle, which means that distance is 1. These two vectors are both unit vectors. They also are perpendicular to each other, because that's how circles work. And that makes these two gray triangles congruent triangles. Yeah? Okay. All right, well, then what that tells me is if I look at the position vector, and if I take a derivative of the position vector, oh, by the way, okay, hang on. Share colors, let's see here. If I look at the position vector, and if I take the derivative, let's see, when I take the derivative, I get the velocity. That's something we know. But I just talked about what the velocity is. The velocity is this vector, and these are similar triangles, congruent triangles, and so I know these two because I know those two, and that blue vector therefore has to be this, just by sort of looking at how the congruences work out. So merely by observing the geometry of the circle and knowing that derivatives are velocities, I get these two statements about derivatives. And you'll notice nowhere in here did I cite any old formulas about what the derivative of cosine is or what the derivative of sine is. What we have here is basically a geometric argument that derives, that sort of proves that the derivatives of sine and cosine are what we in fact already knew they are. Everybody with me? So why do I care about this? Well, because I like it when things are easier to understand as opposed to harder to understand. What previous intuition do you have that the derivative of sine is cosine? Well, you can write down the formulas and you can do angle addition and you can factor stuff out of stuff and look at the certain limit, and you have to make an argument about what's the limit of sine x over x. And frankly, it's kind of algebraic and opaque and not particularly intuitive. Right? This, I think, is very intuitive. Right? Unit speed, parametrized curve, velocity vector, geometry. We're done. This is now officially my favorite proof of these two derivative formulas from Calc 1. Multivariable calculus allows us to make single variable calculus easy sometimes. And this is a great example. Okay. I just think that's cute. All right. Okay, now y'all remember questions like this, I feel sure. Y'all did sort of single variable versions of these a million times. If you know the velocity, the acceleration, you can get from the velocity by taking a derivative. Derivative of velocity is acceleration. So easy little calculus, boom, we've computed the acceleration. Now, what about position? How would I find position? Well, okay, let's back to here. The derivative of position is velocity. Let's say that sort of grammatically backwards. That means an antiderivative of velocity is position. Right? I'm sure y'all remember that from Calc 1. All right, well, so here you go. Take velocity, take an antiderivative of that velocity, and that will give you position. And how do you proceed with this calculation? Well, okay, so here's what your velocity actually is. The velocity is that. And antiderivatives, you do one coordinate at a time. And y'all remember your single variable calculus. By the way, do make sure that you do remember your single variable calculus. In this case, I didn't have to do anything tricky. But I am going to assume that y'all are solid and proficient with standard anti-differentiation methods. So up through and including substitutions and integration by parts. Now there are some tricky, clever, like far out methods. We're not going to use any of that, right? But substitution is really fundamental. You can't get away from it. You have to know it. And by the way, the engineering school has specifically insisted that we keep y'all up, polished up on your integration skills. Right? They specifically told us this. So anyway, make sure that you're good with your integration stuff, and then don't forget your integration constant at the end. Okay, so looking at this formula, looking at that equation, let's ask the question of how do we determine this integration constant. Here's a false statement that floats around. Despite our best efforts to get rid of it, a lot of people think the integration constant has to equal to the initial condition. And that is a bunch of nonsense. It absolutely does not. Which is cognitive dissonance for a lot of students, because they're like, I did a bunch of these in high school and every single time it worked out that the initial value and the integration constant were exactly the same. How could it not always be true if every prior example I've seen, it works? Right? So I'll come back and talk about that in a second. Let me talk to you about how to actually do this. What we're going to do is we're going to plug in t equals 0. When you plug in t equals 0, position becomes 5, 6. This expression, a little arithmetic, plug in some numbers, becomes 3, 1. And of course my integration constant just follows along for the ride. That purple equation now turns into this equation, and that one is easy to solve for C. No big deal. And notice, it is not the same as the initial value. Everybody see that? So what gives? Where did this mythology come from that these have to be equal? I'll tell you where it comes from. It comes from the fact that in a lot of high school a lot of high school single variable calculus classes, the only functions they give you to deal with are polynomials. Which means these functions will always be polynomials with at least one factor of t. And then when you plug in t equals 0, this will always be 0. And so your initial condition will equal to your integration constant. So when the class is a little sloppy and only entertains polynomials, this is the kind of nonsense that can result. Right? So it does not work. And y'all have to make sure to get that out of your head if you have some pre-existing impression that somehow that has to be true. Not only will that give you wrong answers, more important than that, it is invalid reasoning. So I want to make this very clear. Even if you get the right answer, even if the question at hand happens to be one of these ones where coincidentally they're the same, if you don't show how you argued and that you didn't just recopy the integration constant, your reasoning is not valid. That's the problem. The wrong answer is the natural consequence, I suppose, but the reasoning is what we care about. So make sure to don't count on getting lucky, right? Make sure your reasoning is valid. And then I'll cut real quick some equations to look at. A very straight read. It's just one little thing out of the Kepler section. But anyway, all right. Drawing the line right here. See y'all later. Have a good one. See you on Friday.